So can everyone see my slides?
Yes, yes.
Okay, perfect. Lovely. So we're all good to go. So it is wonderful to be here. And I've been charged today with talking about an introduction to machine learning, which is a very sweeping topic. So I'm going to title this talk a short overview of hardly everything, because the nature of these type of intros is that they end up being almost a scattering of interesting factoids. But the hope is that they're a sampler of things which could be interesting to you, and hopefully it sets the scene for the things that you're going to experience over the next few days with the wonderful instructors that you have. So to get us started, perhaps a little bit about me. So I'm a researcher at Google Brain, and my research to date has centered on how do we train models to fulfill multiple criteria. In fact, it really means going beyond things like just test set accuracy. So I'm interested in how do we train models to be compact. So that means, can we deploy them to resource constrained environments? How do we train models to be interpretable, fair, robust? And robustness is very linked to something that we'll talk about today, which is this idea of generalization. This talk, I centered it around really a framing of how did we get here and where are we going, which are two very big questions, but I think we're going to have fun with it. And really, why I chose this type of framing is that computer science history is actually very short, and it's quite exciting as you start and participate in this week-long set of classes to know that you're at a very exciting point in computer science history, because in many ways there's still very large problems ahead of us, as well as a lot has happened in a short compressed amount of time. So what I'm going to do is, we have 90 minutes, so I would be very disappointed if it's just me talking for 90 minutes. So I'm going to do a few things. There's inflection points throughout where I'm going to ask questions. I would like to use mainly the chat. So I would like to, it's a new year, I'd like to encourage everyone to be brave and courageous, and everyone should ask at least one question, and feel free to answer your peers' questions. But also, there are some inflection points that are more open questions. So if someone is able to moderate hands up, I don't know if there's someone here who's willing to do that, but at some point I'll ask a question, and if someone could just unmute people who put their hands up. Is there someone here who would be willing to do that? One of the organizers, perhaps?
Yeah, I can handle that. Yeah.
Okay, excellent, excellent. Because I'm terrible at Zoom. I'm mainly in Google Hangouts, so I would I would fear if it was me in charge of that. So yes, there'll be some points where I'll say this is an open question, so raise your hands, and then we'll see. We'll get a conversation going. Excellent. So the chat is all yours. Please add questions as we go, and I'll pause at certain points. And let's start by talking about why we're interested in artificial intelligence. What does this even mean? Really, to do that, we have to revisit early computer science history, and we have to think about what computers were modern. And here I'm talking about modern computers. Early computing had a very narrow functional purpose. So here, this is the Jacquard loom. Can anyone guess what this is for? What the function of this is? Okay, wow, there's a lot going on. Making cloth, excellent. Weaving, Kyle says. Weaving, Yash says, excellent. You're all very on the money. Excellent first guesses. So the Jacquard loom is often considered the first programmable computer. It created automated textile patterns. What was interesting about it is that although it was called the first programmable, I guess, program, it wasn't very flexible at all. In fact, for the most part, once you bought a Jacquard loom, you just used it for the same pattern, because it was very difficult to rethread. And so this is an interesting example of something which technically had flexibility, but in practice really didn't. What about this, the analytical machine? What was this for? Oh, analysis, Hasnain says. Okay, yes, broad answer. I like it. You bet well. maybe like a calculator. Excellent, Shen. Yes, math, counting, calculator. So I think a lot of people on the money. So this was designed to tabulate logarithms and trigonometric functions. And what's interesting about this is that this was conceptualized during Charles Baggage's lifetime, but it wasn't actually built. And the reason why was that the parts needed to fabricate this machine were not available. The correct precision did not exist. And the electromagnetic technology actually only existed during World War II, when a lot of the technology from radio and telegraph relays was reincorporated into computers which were necessary for cryptography. What about this? This is the Mark I. What was this for? Did Matt, I believe Yash is saying, oh, IBM, on the money, Hope. Okay, so it was funded by IBM. That's a very wise answer. Supercomputer. So this is fun because I guess that technically could be true, but it's a very wide answer. First computer cryptography, it was built, it followed on the heels of cryptography, so it's not a bad answer. So this was actually post-World War II. Well, technically, it actually started, I believe, maybe late 1940s. So perhaps it was decided during World War II, but it was conceptualized afterwards. But this was industry's largest electromechanical calculator. There was quite a lot of criticism about whether it was valuable or not valuable. It was technically used for some of the calculations for the atomic bomb, but it was the size of a large room, so it weighed an incredible amount. It was also designed, the casing that you see that's quite elegant was designed by this futurist designer, Norman Bell Jets, I believe it is. I may have butchered his last name, but he had many wonderful designs, and the whole idea, someone mentioned IBM, but IBM wanted something that looked quite striking because it wanted something futurist, even though it was just capable of computing acting a subset of the things that you would expect from your calculator. Really, what you probably noticed in the 3 different examples of computers that we went through is that the purpose was quite narrow. In fact, this was for a few reasons. Firstly, it was very costly in terms of materials to fabricate these early computers or apparatus. But secondly, software was not portable. So essentially, you were creating both hardware and algorithm were one and the same. And in fact, it was only after World War II that interest was seeded in creating machines that could emulate the human intelligence. And this was really for 2 reasons. The first was advances in electronic technology. So really, we see the switch after World War II from vacuum tubes, which are fragile and tend to overheat and had to be replaced frequently, to transistors, which were much more reliable. So this opened up breathing room with computing power, and people could think more broadly about the applications for compute. The second reason was really that academic work prompted a wider interest. So in particular, Turing really seeded the idea of machines that can think, and in particular seeded the idea of machines that can think like humans. So things like the Turing test, which we'll talk about in a little bit, really gripped the imagination of a lot of academia. And then we also had the contributions, laying some of the theoretical contributions for information compression. What is the minimal sufficient amount to encode a signal? And this culminated in the Dartmouth Conference, which was in 1955. This was really, in retrospect, it was a small gathering, but it was the first, I guess, official meeting point for people interested in this idea of imparting to machines the ability to solve problems previously reserved for humans. An attempt we made to find out how to make machines use language, form abstractions and concepts, solve kinds of problems, and improve themselves. And here I want to pause, and I want us to engage in a little bit of conversation, because is it reasonable to center our discussion of AI around human performance? And to frame this, perhaps it's interesting to note that we've always had an idea or fascination with making inanimate objects more like humans. This is not intrinsic to the notion of machine learning or AI. So this is a picture. What is the commonality between the rocks in this picture? Oh, Julian on the money. Julian says faces. Yash. Okay, yes. So this is the Museum of Rocks in Japan. And you'll notice that Christian says looks like human faces. Indeed, it does. You'll notice that all of these have what we seek or kind of project upon the rocks as human faces. And this is actually not an isolated incident. We tend to want to see faces in objects. In fact, there's an entire Twitter account about seeing faces in inanimate objects. And that's largely because we're fairly egocentric as a species, where our intelligence is far more collective than individual. We tend to seek or we have this remarkable ability to remember a large amount of faces, and we tend to largely see ourselves in many different objects. But for a long time, we've also projected that as making inanimate objects more human. This is Pinocchio. This is Frankenstein. These are, of course, examples from our popular culture. And some of that crystallizes what we call automatrons. So these are inanimate objects which are made to trick the human into thinking they're more human-like than they actually are. So this is the digesting duck, which was from 1739. And the digesting duck was created to look as if it could digest, eat, digest, and defecate food, and trick a human to thinking it was possible. This is Mechanical Turk, and what this apparatus did was it was a ploy to convince a human user that they were playing against a machine, but it was in fact a human who was hidden within the apparatus who could play the human. So it was a foil. It was a fake automation. But these were endlessly intriguing and entertaining to humans because it had the allure of an inanimate object that had intelligence. And so when Turing kind of crystallized the idea of intelligence as an imitation game, it fit into a wider pattern of us seeing human intelligence at the center as superior to all other types of intelligence. And the imitation game, someone already mentioned Turing in the chat. Who knows what the imitation game is? What is the imitation game? Yay. Okay, excellent. So it sounds like this may be, okay, Rocco is in on it. Excellent. Chen says the test if an AI is, okay, so a few people have heard of this. This is great. The themes that are coming out is that this is a test. It's a test of if a computer has what was sort of at the time as human-like intelligence. And the test is, as Nia is saying, is that if the computer can outsmart the human judge. So here in this picture, you have client A, which is your computer. You have client B, who's a human, and you have the interrogator. So this was actually based on a parlor game at the time, which was you have a man and a woman and a judge, and the man has to imitate a woman, and the judge has to see which one is the man and which one is the woman. And then it was reincorporated as this Turing test where the interrogator is trying to decide which one is the computer, which one is the artificial agent, and which one is the human. And what's interesting is within this paper, Turing gave this example of what would be a possible interaction between the agent and the interrogator. And what do you notice? Do you notice anything odd about this exchange? Yes. So Abuselai is saying this is also called the Turing test. This is also called the Turing test. Yes, and it's being formalized as I guess perhaps it's an annual, I'm actually not sure, but I think it's an annual test where actual agents compete to see who would pass. So what is odd about this exchange? What about now? What's odd about this section here? The pause, not quite, not quite. seems out of place. Not quite. It's wrong. Yes. Adam said it's wrong. Sebastian said it's wrong. The answer is wrong, Alfredo. Yes. So the answer is wrong. And that was odd given that this was written by Turing, who was a mathematician. And many sources have suggested that what Turing is actually pointing out is that for an agent to convince someone that they're human, they have to make a human error. And this is a very interesting thought, because this perhaps highlights what is tricky about basing intelligence over human, on a human, because you get both the strengths as well as the weaknesses of our intelligence. And in fact, we're fairly bad on the spot calculations. Our thinking is heavily parallelized, and we struggle with things like computations, even though our sight is fairly instantaneous. Identifying objects, for example, takes very little mental faculties. What is fascinating is that, as I mentioned, the Turing test is being formalized as this type of competition. And the first bot to pass the Turing test actually heavily leaned into human error in order to be credible. So this bot, which was named Eugene, posed as a 13-year-old Ukrainian boy where English was a second language. So in terms of our goals and our idea that we actually want to impart to a machine a way of thinking or navigating the world, this is clearly not the way to do it. This is clever programming, but it's not really achieving what we state as a goal. And this kind of points to the trickiness of the overwhelming focus of AI research as being emulating human intelligence. This partly reflects philosophical thought on what is consciousness. So many philosophers see language as a key moniker of intelligence that differentiated us as a species from animals. But it's not clear that our intelligence is comprehensive or complete. So for example, this is the mantis shrimp. The mantis shrimp has 12 color channels instead of our 3 RBG color channels. This is hummingbirds who can see infrared color channels, which is fascinating. And so they see an entire dimension that we're not able to see. Even cows have a very different type of sense. They point on average to face north. So they have a natural magnetic impulse. And these are senses that we do not have, or that are not heightened in our own intelligence. Even Turing was willing to acknowledge this. He said the idea of intelligence is itself emotional rather than mathematical. The extent to which we regard something as behaving in an intelligent manner is determined as much by our own state of mind and training as by the properties of the object under consideration. And so in many ways, our bias when we do research is that we only have our own faculties to navigate and to shape the world. And so to see a different truth in the world is actually quite difficult, because we're governed by our perceptive faculties. What can we see? What can we understand? The idea that perhaps computers would augment rather than imitate our intelligence gained ground in the 1960s. So there was a fascinating paper about man-computer symbiosis. And in fact, in many fields, we now talk about artificial intelligence as augmenting rather than trying to emulate human intelligence, to do the things that we're bad at and complement our own intelligence. But what you'll see is, which is interesting, is that despite this more holistic view, much research has continued to center on beating human performance. So this is Arthur Samuel checkers with no date. Ooh, I believe it was, someone should spot check me. I believe it was 1950s. I think it was. It wasn't 60s. Yeah, if someone is quick on their Google searches, you can put that date in the chat. But then it was Deep Blue in 1997. You'll notice that both are essentially agents trying to compete against a human. Through to current day. So this is Go and this is Dota 2. I was actually in the audience at Dota 2. So perhaps If you peer very closely, you'll see a spot of red somewhere. But these are, again, agents competing against human performers. And 1956, thank you, Nia, thank you, Kevin. So it was in 1956 that Samuel Arthur beat Checker. And why do we do that? So I discussed perhaps the reasons why we might not want to do that, but nonetheless, we still do. So one reason is what we call the need to measure progress. And it's often hard to measure progress if you yourself cannot measure it. So often focusing on these well-defined problems is a way for researchers to try and tackle what we call a toy box first, with the hope that that generalizes to a larger problem. So McCarthy here says problems are well-defined where there's a simple test to conclude where a solution is solution. People solve problems by searching through a problem space, and they will both these quotes are talking about, at the time, symbolic approaches, and we'll talk a little bit about more about that in the next section. But this has persisted. So this is David Silver. He was talking at the Deep Learning Indaba, and he also is a big fan of controlled environments in which to measure progress. And the reason being is that without a controlled environment, you can end up having diffuse research focus. And so you can end up essentially not having a clear way to compare work or to understand which research directions are promising. The caveat, of course, is that you can end up pursuing the wrong research focus for an extended period of time, or you can end up choosing an environment which does not generalize. So you can end up spending a lot of time in a simulated environment, which fails when it goes to a more complex environment. And this is a balance that researchers struggle with, and sometimes we get it wrong, sometimes we get it right. Recently, the ImageNet, for example, is an example of a benchmark which emerged in the 2000s, which is still heavily used, but there's growing consensus that it's saturated as a benchmark, that there are limitations to how we can show progress on that type of data set. So this is perhaps a good way to round out this discussion, is that we have now explained why AI is exciting, but we've not said what it is. We should just say, well, it has to do with smart programs, so let's get on and write some. So this is tongue-in-cheek, but I do think carrying an awareness that focusing solely on what is human aligned is an incomplete view of how we measure progress in this field. And in fact, this comes up a lot within my own field of research of interpretability, because often when we think about interpretability, we think about what does a human trust, what matches their value judgment. And I believe this is the incorrect way of seeing things, because often when we are trying to interpret a model, it may not align with our judgment, but it may show us a new mapping or way of doing things. One of the things I find interesting is for things like Go, a lot of Go players watch AlphaGo videos on YouTube because they learn something from the way the agent plays that's different from their own play, and that's different from any play that they've seen before. The same way that when we have a model which is essentially classifying retinopathy, a lot of doctors have learned from the model's classification that is able to discern things like gender or whether the patient has smoked just from that photo of the patient's eye. These are details which the human doctor could not pick up on, and they're largely because some of our convolutional neural networks can do these pixel-wise comparisons. So perhaps you've gathered from this conversation that AI is a goal rather than a methodology. In a short history of computer science, there have been several reigning paradigms about how best to achieve that goal. So today we're going to talk about two. And the main reason is that much like the length of computer science history, which is modern computer science history is quite short, understanding the transitions between the two will help you understand a lot of how short the history is, as well as how many open problems there remain to be solved. One thing to note is that consistent across these two paradigms, progress is centered primarily on solving subtasks. So you break down this monolithic task of creating thinking machines into subtasks. That could be computer vision tasks, natural language processing, robotics, games, audio processing. And it's worthwhile noting because this is very different from our own intelligence, which typically combines inputs from multiple stimuli to form decisions. So, for example, if you are at home and if you can, dig your toe into your whatever floor is underneath you and touch your fingers together and try and do it at the same time. So if you do 1, 2, 3. So did you feel that at the same time? Did you feel both your toe and your finger at the same time? Yes. Yeah. Oh, yes. Actually, Joshua, that's a very good answer because it's very hard to know because most likely you felt it as a mush of feeling. And that's largely because even though, yeah, good answer, Shin. Yeah. Oh, Viveka says sequential. Wow, you must have remarkably perceptive tactile touch. What's interesting about this experiment is that most people don't know, or they say, yes, it was at the same time. Because even though your toes are much further away than your fingers, the way that our brain maps stimuli is that it tries to wait for the shortest signal. It's also why in the early days of broadcasting, it was discovered that as long as video and audio arrived within a 100-second, I guess, interval, viewers' brains automatically resynchronize the signals. And even now, unless that interval is passed, you will not notice the difference between a video lag and an audio lag because your brain just waits for any signal in that interval and kind of mushes them together. And that's largely because our reception, our prediction of the world is largely based upon a combination of stimuli. So the same way that your taste is largely also influenced by your smell, we have certain pathways which mush together in order to form a certainty about the world around us. And so there's not, in fact, many researchers are extremely excited about multimodal models, and there's exciting research in this direction. The reason why it's recent is because of the computational cost. So even to get to the point, and largely why all these subtasks were broken up into different fields, was a computational problem. Tackling any one was seen as a significant challenge. And it's only very, very recently that there's several teams who are thinking about how do we combine multiple stimuli to form a more grounded, a more anchored view of the world. But on, pardon?
We have a raised hand.
Oh, excellent. Yeah, please go ahead.
I think you should be allowed to unmute yourself now. This is Eli, I believe. Sorry, Aaron Ma.
Oh, sorry, I wasn't intending to ask a question. Oh, I'm sorry.
Oh,
apologies.
That was an excellent demonstration of the raising hand functionality on Zoom. So thank you, Aaron, for demoing that, even though unintended. So now we know someone can raise a hand if you want, and you will be seen. I'm going to continue on for a little bit, but please do add questions. I think I'll stop at the next section and go back through the chat and answer some of the questions. That feels like a good place. And then we can have raised hands experimentation again. So in the 1950s through 60s, I've already alluded to this, but we had this switch from this narrow purpose computing to these symbolic approaches and expert systems. And the basic components were you had some type of database with facts and rules, an inference engine, processing consultation, and an input-output interface for interactions with a user. This is kind of a spin on that in definition, but expert systems were a subset of symbolic approaches. So you could have another, I guess, subset task of symbolic approaches was search, which was also kind of a big subfield of research. But these overarching approaches were characterized by consisting of a logic component, which specifies the knowledge to be used, as well as a control component, which determines the problem-solving strategies. And a great example of this was Eliza. So Eliza was a mock Rogerian psychotherapist. And I think the best way, so what's fun is if you go to this link, you can actually play with Eliza. And I did so earlier today. So this is my conversation with Eliza. What do you notice about this conversation with Eliza? Yeah, Greg's right. She's repeating back what you say back to her. Yeah, it's a Q&A. She repeats the question. I do like that. Someone says she hasn't eaten breakfast yet. Excellent. Yes, I mean, it's absurdly nonsensical. So if you give an input like this, which I'm assuming not many of her cases were complaining about not eating breakfast, Eliza essentially responds with an open-ended question. So Eliza was not a machine learning algorithm. Eliza was based on a series of heuristics and rules based on a type of psychology that was called Rogerian, which was meant to be about echoing back to the patient to begin with. So in many ways, it was very much in the spirit of this subfield of psychology, but it ends up being fairly ridiculous if you give a kind of prompt that's quite specific, like I did. And this highlights, in particular, the cliffs of algorithms like this, and I hesitate to call it an algorithm because it's not quite a learning component, but of a framework like this for assessing inputs or producing predictions. And really, this was the shortcoming of symbolic approaches. So it required that expertise could be verbalized. And that's why some of the most promising symbolic approaches were expert machines that focused on domains which had been heavily documented to begin with. So something like healthcare, where there's already a large amount of documentation which is designed to teach humans how to become doctors, that was where it showed the most promise, because there's already a lot of perhaps decision tree style rules that doctors tend to follow in arriving at I guess, decision about what the condition is. It also leveraged transparent modeling techniques to solve the problem. So Eliza, for example, had a lot of hard-coded heuristics. There was only a certain amount of ways that Eliza could answer a prompt, combined with logic and search. Checkers with the correct date this time is another example of this. A lot of the promising, exciting developments during this era were around games and game solving. And for something like checkers, where there's a more limited search space, it's not as complex as something like Go or Dota, these type of approaches could actually work. So you could have breakthroughs, because you could have a search small enough where you could essentially use logic-based techniques, backtracking, trials to figure out a way. And so with these symbolic approaches for search, you did move away from rule-based programming. So it was different from the earlier computers we saw, which were very narrow and hard-coded. You didn't have to explicitly program the maze. You could allow for these aspects of backtracking and search. And if many of you have done algorithms classes, you've probably already come across some of these maze navigation algorithms. But they're not typically what we think of as machine learning or promising AI algorithms today. So by the end of the 1980s, there were clear limitations to symbolic approaches. And one of the biggest ones is that it really depended upon vocalizing what knowledge is and how we do things. So this is a fun video by one of my colleagues that actually came out very recently. He works in robotics, and he was trying to articulate how difficult it is to actually encode the knowledge of what we do without thinking. So the video is titled 14 Steps to Opening a Bag of Dates, and I've included 6. But his point is that we do a remarkable amount of really important gestures and manipulations that we can't express, because even slowing down slow enough to be able to articulate it takes much more mental work than the reflexes, which become ingrained. And this really was the cliff of symbolic approaches, because if you have to articulate everything, it limits your search space of how much you can navigate the world. So I'm going to pause here. I'm going to invite some questions. So if you want to ask a question, please raise your hand. Be courageous, new year. Otherwise, I'm just going to scroll up. So Jayla says, why is the question not answered? So I presume that she's referring to a question, or he is referring to a question further up. So if the artificial agent passes the test, could it be used to test another artificial agent? Yes. I guess what you're describing is a meta approach to testing intelligence. So one parallel, which is interesting in recent research, is that there has been research around asking agents to learn a joint language. So typically, a lot of natural language understanding has focused on, can agents or models learn to generate a distribution of language that is ours? So one form, one language that we speak to each other. However, there is a separate research track, which is considered the possibility that we just want to look at emergent communication. And emergent communication here means we just want to see, can you compactly have agents actionably communicate with each other to perform tasks? This, unfortunately, I know the researcher involved, who's very lovely, but unfortunately that paper took on a doomsday spin, because it was, I remember it appeared in the news as agents learn how to communicate humans can't understand the language. So what the agents did, quite understandably, if you understand compression, is that they formed a language which was far more compact than ours. And so it was incomprehensible to humans. And so interpretability was violated, which meant that humans did not trust the language. So yes, you could conceivably have another agent test another agent to see if it's intelligent. It's unclear if we would ever know if what had transpired in that conversation to persuade the agent of intelligence. But it's an interesting question. Do we have hands up, or I'll keep on scrolling through to get one more question?
We have one, just a second. Soroisi, I'm sorry, I probably mispronounced your name.
It's Saoirse, thank you. I had a question about heuristics. So with like the LISA program, you said that the heuristics were hard-coded. So then in like an artificial intelligence algorithm, would it make its own heuristics, or would it be given like general heuristics and then like build off of those?
So it's interesting. I guess what you mean by artificial intelligence algorithm, perhaps you're talking about this next stage, which is machine learning algorithms that we're about to go into. So typically, heuristics can be used also as an evaluation measure. So you could have a heuristic of what you think is a good objective, and then use it to evaluate, but the model learns how to optimize a function to map to that heuristic. But what was happening here was that even the mapping itself of how you get from the input distribution to your prediction was also a rule-based heuristic of what we codified as knowledge. So that is different. So when we talk about machine learning algorithm, there is some learnable element. So the model will learn based upon some type of objective, which could be, a notion defined by us of what is good, but a model will learn to optimize for that. And so that part, we delegate learning to the model itself, and we don't hard code anything.
Okay, thank you.
Yeah, good question. Okay, there's two here, so I'll take one of them, and then we'll press on, and we can get to the exciting present day. So, Kevin has an excellent question, and then we have an anonymous entity. Oh, that's always exciting. So, okay, so let's start with Kevin's question. Was the communication between the agents truly a threat? No, I think this was a great example of how we as scientists need to be better communicators, because it was a natural product of the optimization process that the researchers had set up. So if you don't add any constraint on the unit of communication, if agents can efficiently communicate in a much more compact representation, then they will. That doesn't necessarily mean that it just means it's not interpretable to us humans. But this was in a research setting. It wasn't. It wasn't at all linked to something where human welfare was at stake. And so I think it's a great example of how there's a large gap right now between the work that we do and how we need to communicate our work to inform scientific discourse as well as public discourse and policy. But to answer shortly, no, it was very overhyped. And the poor researcher, who's now my colleague, he just shakes his head when you ask him about the paper. He's like, oh, don't want to go back. Okay, so anonymous attendee. Are there machines which can trick up to a certain age? There's no bounds on the rules. This is why this 13-year-old agent was described as a Ukrainian boy, but it's not in good spirit. So if you think about the spirit of the competition, it's almost like clever hacking, I would describe this as. And I would say most researchers felt that it wasn't in the spirit of the competition, that this was the bot that won. Okay, let's press on. Present day, focus on machine learning. So this really goes back to the question that was asked. So what is machine learning algorithms? How is this differentiated from these hard-coded rules and heuristics? So we allow machines to learn from experience. So we avoid the need for humans to specify all the knowledge. We may specify part, which is the objective, and we may specify things like hyperparameters, so the training regime that gets us to our final function. But we allow the machines to essentially learn from the data distribution and update their weights if it's a parametric model, or update their functional form in order to hopefully generalize beyond the distribution that we've trained on. So that means that we have to also collect often an adequate amount of data. So Arthur making a comeback with a quote. So he defines machine learning as a field of study that gives computers the ability to learn without being explicitly programmed. And it's really important to note that neural networks are only one machine learning technique among many. So there's plenty that are actually going to be covered over the next few days. Linear models, logistic regression, naive Bayes, bag of words. And the other thing, I guess, words to the wise to think about is that typically adding complexity is the way to go. So starting with a simple hypothesis about whatever problem you are trying to solve and progressively adding complexity provides a rigor to your approach and justification to why you choose certain tools. So I would always recommend, when you're approaching a new machine learning problem, start with your assumptions about the data set and also the data sample size, and start simple and progressively justify why you're adding more complexity to the functional form. And we'll talk a little bit about that. But I've been charged, since your first lab is a very exciting core staple of any researcher's journey, which is MNIST, I will be talking about computer vision. So we'll start with this case study of computer vision, and I'm going to use that to talk about the transition from symbolic to machine learning to deep neural networks. And then we can also talk about, why did it take so long? So why did we have symbolic approaches which clearly didn't work for so many decades, and now we've completely switched to a different type of approach? So we're going to be learning about a problem researchers have been dedicated to since the 1940s. So computer vision is a difficult task, both because of the high dimensionality of the input space and because the human visual system is extremely effective. It's fun to first think about, what do we mean by computer vision? Because firstly, we need some type of data representation for what we see instinctively through our ability to process light. So our eyes are processing light and gleaning from light different color bands, different ways to discern the world. But codifying that into a technical object, which is able to store a reasonable impression of what we see, was a miraculous feat in itself. So this is the first photograph in 1826. And then we have the first unintended photograph of a human being. You may be able to spot the human being in a very, I guess, buried corner. First selfie, very severe. This, I think, I believe this was like a long exposure time, and so part of the expression was that he had to remain remarkably still for a significant period of time. First moving picture, and the first digital photograph. And the first digital photograph is important because it's largely why we have such a body today of interesting data that we can try and translate into a reasonable representation. And what's interesting, going back to our early conversation about human-centered, is that cameras in themselves are heavily optimized to us and our perceptual vision. So the way that we see the world is actually not how the world is. We have, for example, log scale vision, so it takes a noticeable change for us to register. So a lot of improvements in camera technology have been slowly optimizing what is the raw input, which is how the world actually is, to fit our perceptual system. And so already in our data set, there's a bias in terms of how our data is structured. There's also a bias in terms of how we take photographs. So you'll notice the first selfie wasn't smiling, but progressively we've essentially treated humans in a camera as it's often odd not to smile. And we have other biases, like even if we're taking a photo of an object, it's typically centered in the scene. This will come up later on because convolutional filters, which we won't be covering much today because you have an entire lab on it, but convolutional neural networks, convolution filters have a center bias because of the way that they've been structured, unless you do padding around the edges. And this works because we typically don't photograph objects in the corner, or if we do, they're not the object that is labeled the image. But if we were taking images in a more natural way, so if you get into the area of like self-driving cars where you're just streaming images, then it becomes much more of an interesting problem where all the models we've optimized on photographs taken by humans where everything's centered don't generalize as well. And this is all very interesting to be aware of as researchers or embarking on your machine learning journey, because how we think about how to model the distribution depends very much on the distribution itself, and understanding both the biases and the limitations of the distribution itself. And so when we talk about computer vision tasks, we can talk about things like image classification. So we're trying to identify an object in the image, object localization. So it's not only identifying the object, but where it is. Object recognition, where you want the whole suite. So you want to do both object as well as locate both. And I mentioned that this is considered a difficult task. So the high dimensional input space is it's a large reason why computer vision was tackled subsequent to audio in a lot of the earlier research, because the computational power needed was prohibitive. And that's largely because a single image is associated often with 250,000 features. So if you store a short image as a 3D matrix and it's 255 pixels by 255, you end up with 250,000 features. And when you scale this across a data set, you can start to understand why processing and extracting features was very difficult. And we also end up with a lot of variation in images. So out of curiosity, if we look at the these images, which ones do you think are going to be more difficult for a model to classify? I wonder how I can get my chat back. Let's see. It's intriguing. Oh, here we go. Lovely. Okay, so people, okay, so a lot of 4s, a lot of 3s. Okay, 3, 4, 6. People are throwing in a lot now. 5. Okay, so we got a lot of 3s and 4s. Why 3? Okay, I like, Shani says possibly 5 because of the lighting. Okay, good, that's a reason for 5. So then for 3, a lot of people are saying I can't see the face, can't even make out what it is. Okay, what about 4? Chaz says the perspective is unusual for 3. Okay, so now on 4. Cat thumbs into the background, cat's too small. Excellent. Okay, so I think you've hit on a lot of what is interesting, which is that 3, it is an odd perspective. Someone said that. It very much is. We're typically used to seeing, well, actually, here's a question. What do you think is easiest for the model to recognize? 5, 6, 1, 6. Interesting. Okay, 1. Whoa, a lot of people saying 6. That's intriguing. Why 6? Clear view of face. Okay, that's solid. Okay, so I think what a lot of people are alluding to is in fact very true. So we may have in 1, we may have this very frontal view, which is very typical of a well-centered object. In 6, we have a direct view, so we can fully view the object in question. In 5, someone mentioned straight off the bat that the lighting is poor. So this is what I would call high contrast, or it's saturated. I actually don't know which. Perhaps a photography expert can tell us which, but there's a filtering element to it, which is out of distribution given the rest. Okay, so Dylan says 5 is saturated. Excellent. I'm glad we have a varied expertise amongst us. And then 4, what you can see is, as many pointed out, it's actually very hard to even tell what is cat, what is blanket, what is sofa. So all these are very difficult. What's fascinating about our vision is that we're quite robust to all these translations. So we're robust to viewpoint, to scale, to illumination. If I were to ask someone on this chat, what is this? You would probably still say a cat. You might not know precisely what species, but you would still answer correctly as it's a cat. And that's why it's a hard baseline to beat. And in fact, that's why progress on it was over such an extended period of time. So the task, what type of task is this? This is a good sanity check on where people are. Is this, what are we trying to do? Is this a regression task or is this a classification task? Okay, lovely. A flurry of, yes, okay, good. So this is a classification task, and that's because we're predicting essentially what category an image belongs to. There are possibly, you could construe this possibly as a regression task. Maybe you would try to predict how many colors are in each image. But today we're going to treat it as a classification task. And we're going to treat it as a supervised learning problem. There are also a lot of recent progress on unsupervised approaches to image classification, but we're not going to touch that today. We're just going to talk about this structure of a supervised learning problem, and talk a little bit about the history and how we got here. And so when we have a supervised learning problem, we have a label associated with each image, and we have a single input example and a training data set. So our training data set consists of an image and a label associated with each image. And so before 2012, this was really a multi-step approach. And so often you would have machine learning components, but they'd be handcrafted. And what I mean by that is that you would have things like, you would have an encoder, and I'll kind of build out what I mean by encoder, which would learn a representation, and then you would have this linear model at the end. One example of encoder would be handcrafted human feature engineering. So you would just extract a histogram of the pixels in the image, and then you would have a linear model after that trying to classify it. So essentially what that is doing is if it's blue, you'll have a histogram which is skewed towards a pixel distribution where it's blue. And then the idea is the linear classifier would learn to recognize, oh, that's likely a shark. You have, of course, much more sophisticated. The 2000s were exciting because there was a lot of research that was doing very interesting things with these handcrafted features. So you have things like the so-called edge filter, which is doing something very similar actually to what a convolutional filter does in a convolutional neural network. So it's kind of highlighting the edges. You have a hog filter, and what's interesting about this is that some of these features were very effective, but it was difficult to generalize. So you could have something that was extracting useful features for facial recognition, like it would identify a nose based on the space, but it was hard to generalize that to classifying a snake. And also encoding was separate from the classification model. So you have this whole pre-extraction phase, and then you have your classification stage, and often this required several different iterations. You're extracting different features at different places. And of course, the goal of feature extraction is to downsample heavily. You want to get from that huge grid of pixels to something far more manageable. But it often separate features required separate independent training. So often you would extract different features and then combine it all in a linear model. So all this was fairly labor intensive, and it required a lot of human judgment. So we're still not completely departed from the symbolic approaches. We're still kind of tinkering, so to speak. There is a learnable component, but we're doing a lot of handcrafted feature engineering before we get there. What was interesting is that really in the 1990s, we had some exciting breakthroughs. So we had Linnet 5 and was trained successfully on MNIST. And I want to tell you a little bit about MNIST because you're going to play with MNIST later today. And MNIST is I guess it's a bread and butter of computer vision research because it's very manageable. So MNIST is a 28 by 28 pixels. So earlier we talked about 255 by 255. 28 by 28 is far smaller. So it requires less, the dimensionality is smaller, which typically means it requires less parameters in order to run a useful representation. It's also quite a simple data set. It's digits that are numbers. And so the whole goal is, can you recognize an image of 4 and classify it as such? The third aspect of the efficiency is that it's black and white. So typically your natural images will have 3 at least color channels, RGB, and MNIST is black and white, so it doesn't have color channels, which again reduces the amount of features that you have. Because of this, there's been many popular variations on MNIST, such as Fashion MNIST and K-MNIST, and it continues to be a popular, I guess, toy problem set now as researchers are trying to experiment with the ideas. So often you want quick iteration as you explore ideas, and so you'll start with MNIST and try different combinations out and then progress to something more complex. The difficulty with MNIST is that it's also being shown to work for problems but then not translate to natural image data sets. So often there's findings which have been shown to be true of MNIST, but often stumble when you try and translate them to larger scale data sets. This is, of course, a balance because we try and balance it with the computational cost of our experiments. And I think it's interesting as you go on in exploring problems, there'll be a natural sequence where you'll start with MNIST, you might do C410, you might do C400, and then perhaps for a few experiments, you may scale to something like ImageNet or something larger. But now we're going to talk about 2012, because this is really where convolutional neural networks finally prove themselves empirically. And convolutional neural networks differ from the approaches that we described earlier because it's a single differentiable function. So it's end-to-end classification pipeline. And what that means is that we delegate representation to the model itself in its entirety. So in fact, the model learns what to extract in order to arrive at a correct prediction. And so this is an advantage because it doesn't require independent training, but also empirically it turned out to work very well. So in 2012, AlexNet outbeat other models, I believe, by reducing the error by 12.9%, if I'm correct. Someone can spot check me. And what was interesting about that is that overnight, basically, most people switched to convolutional neural networks. It was an astounding empirical success. And why? So why was this possible in 2012? And so there were a few features that are now very ubiquitous in convolutional neural networks that allowed for enough downsampling to allow for efficient training. So shared weights, local connectivity, and downsampling through things like max pooling. I'm briefly going to talk about them here, but not too much because I think you're going to get into this later in the week. But I do want to mention that essentially what is interesting about CNNs is that it exploits our knowledge of natural image properties to speed up training. So if you look at an image like this, so if I'm here, and this is a patch of pixels, is this pixel different from this pixel? Am I extracting a different feature? Ooh, Barack says yes. DK says no. Okay, this is controversial. So why yes? Technically yes. No if it's generalized. Oh, Kevin. Okay, intriguing. What does that mean? It sounds like we need some hands up. So who would like to speak on behalf of yes? Be brave. Okay, Daniel's up.
Hi, can you hear me?
I can hear you. Yeah.
Okay. So I would say that that you're not extracting different features because, again, if you're to compute the Laplacian of that, I feel like it would be the same pixel value. So you're not really extracting anything. Like the RGB values are pretty much the same.
Okay, let's hear a response from the no. Kevin's up.
So I think it's no, technically speaking, because I doubt it's the exact same pixel in terms of value, considering we see that there's some kind of shade going on there. But if we define feature as like an image, something more logically, something like a component that makes the picture itself, we would say that it's just grass or it's just a background. So it depends on how we define what we're talking about. So
Yeah.
that's what I'm thinking.
Yeah, those are two excellent responses. Kevin, you've captured the nuance of it. So yes, if we were being precise, they would not be the same features. Likely, they are slightly different pixel values. But we're interested in efficiency. We're interested in getting to the core. We just want to know if it's a dog or not a dog, or perhaps if it's a dog or 999 other classes, because I believe this is an ImageNet class, which has 1,000 classes in general. But to get to that, all we really care about is getting a sufficient pulse on what features are present. And if the features are very similar, which often happens in natural images often we have contiguous patches, which are similar information, then we should exploit that to reduce that. Because if this is green and this is green, if I have a filter here and it just extracts the pixels there largely green, then that's still informative. And in fact, we found that it is informative. Is it a precise mapping of features? No. But to do that, we would need something like a fully dense layer. And that turns out to be extremely computationally expensive. So both very good answers. Thank you for raising your hands. And the other property that we like about the design of convolutional neural networks is that sharing weights provides translation invariance. So for example, if a cat is positioned over here and a cat in a different image is positioned over here, we still want the model to be able to classify cat. And what we find is by having the filter essentially essentially roll over our input frame, we're extracting the same feature at each point. And so because of that, no matter where the cat is, the model learns to be extracting the same features. So it learns to be translation invariant. And this is a very important property. And the final thing, which I don't mention here, is this downsampling, this aggressive downsampling. There's a question here. CNN allows to recognize the cat if it's upside down. Yes. So this is actually a very interesting question from Christian, because perhaps Christian doesn't know he hit on the jackpot, but this is actually a very timely question. So there's an advance upon convolutional neural networks, which is called capstone networks, and it's by a researcher who many of you may know, but Jeffrey Hinton, and also the first author was Sarah Sabor, Nick Frost, I believe, on the first paper, and their paper was really to address some shortcomings of things like translation invariance. They're also quite grumpy about max pooling. So Christian's question is, CNN allows to recognize the cat if it's upside down. So yes, the answer is yes. And what Sarah and Nick and Jeffrey said, they would say that this is actually a shortcoming of convolutional neural networks, because it's nonsense to have a cat upside down. And if a cat is upside down, the model should just return no answer. but because of the way that we've codified it, it will still return an answer. So their proposal was to do capstone networks. And capstone networks are a very interesting solution. I suggest you read the paper. Capstone networks, actually, I often talk about because they're an example of an architecture which actually doesn't play well with our current hardware. So even though they have very interesting properties to solve some of the deficiencies of convolutional neural networks, they're very hard to train on accelerators that we currently have, like GPUs or TPUs or other optimized hardware, which has made them less, I would say, it's been an interesting example of what I'll talk about a little bit later, which is the interaction of hardware with what ideas succeed and fail. So that was a great question from Christian. And max pooling, by the way, has the same shortcoming or grumpiness, because max pooling, although it's not covered here, is this idea that what you take is when you have a certain intermediate set of activations, you just take the maximum activation. So all you propagate forward is the maximum value. And what's interesting about that is that it actually throws away a lot of information. So it's a fairly aggressive imprecision. So earlier we talked a little bit about, Calvin was talking about what's not precise because they're not exactly the same pixel. So that's one type of throwing away information where we're not exactly getting the preciseness of the feature, but we're assuming that there's some type of local semantic similarity, but this is a much more aggressive form of not being precise because you're essentially throwing out the lot except for the max. And it's interesting that it works so well. And in fact, that's one of the comments from the authors of the capstone network. It's a shame that it works so well because it's not rigorous and it's not theoretically sound. It's a very interesting area of open research. So I'm going to keep on skipping along because these are very interesting questions. So here's some use cases. So this is tracking population of elephants in remote areas. This is by Benjamin Akera. So he was part of the Kampala lab. He's now a PhD student at Mila. He's detecting crop disease in cassava, a lovely researcher. This is reporting traffic accidents real time in Sudan. Detecting informal sediments. This is Philmon, who is doing plant classification disease identification. And this is Victor, who's doing a variant of essentially structuring CNNs to do generative distributions. So why did it take so long for deep neural networks to be recognized as a promising research direction? So perceptron hardware, which is a single layer feed-forward network, was released only a year after the Dartmouth conference. In fact, many of the components for deep learning were already in place. So backprop was invented not once, not twice, but 3 times in 1963, 1976, and 1988 independently. And convolutions was proposed in 1982, but was combined with backprop in 1989. However, deep learning was only really accepted as a promising research direction 3 decades later. So the question is why? And the reason why I included this in this overview is because I think that understanding the mechanisms by which progress occurs in a field is actually very important starting out. So you can have a critical eye and understand that science is not a frictionless marketplace. In fact, the way that ideas progress is often quite noisy. And as we contribute to a field of research, often we need to have essentially a type of stamina for pursuing ideas and thinking about how can we reduce the friction in this marketplace so that good research directions can surface and we can accelerate the iteration pace. Danush says the big data revolution. So yes, so Danush is getting ahead of the crowd. He's answering the question why. So you're welcome other people to join in. Danush, you're correct. So part of it was the collection of annotated data sets. So I mentioned ImageNet, but even curating something like MNIST and then progressively further data sets, we now have a kind of a plethora of data sets for different domains, has been very important, not just in terms of the amount of data available, but to also focus research efforts so that we're using the same benchmarks and we're measuring progress along the same dimensions. It's actually a critical part of building up a body of knowledge as the scientific tooling. Jed says very computationally expensive and hardware was not advanced enough. Okay, excellent. Jed is getting at one of the points that I've mentioned here. The first one actually is that insufficient uptake of work on connectionism. So this was proposed by John Holland, and when asked like why were we in symbolic approaches for so long, his response was that essentially there wasn't a forceful advocate. This was partly because of the reception of the first perceptron network. So there was a combination of overhype. So it was published in the New York Times as, you know, this new Navy device will basically solve everything, but also very critical. So this kind of, I guess, galvanized the community to reproach that it was sufficient to do everything. And so we had a lot of literature which essentially said this couldn't even map simple functions. So a good example is the perceptron was a linear function. And so for something like XOR, you can't actually form a useful decision boundary. But to Jed's point, hardware and software were really tailored to symbolic approaches, both because there was not much computational power available, but also a lot of hardware was not really tailored to architectures like deep neural networks, which essentially needed far more effective flops, so far more memory, and were only really effective when there was distribution. So universal processors like CPUs are poorly suited to deep neural networks. So CPUs incur high memory cost on parallel tasks. This is called the von Neumann bottleneck. Essentially, the key limitation was you couldn't train networks that were deep enough. And the need for parallelism of operations was pointed out as early as the 1980s. However, both because of the fact that experimentation and hardware was very expensive, as well as because Moore's law was still in full force, so you were getting predictable increases in compute every 2 years, it deterred experimentation. However, what is really fascinating about this is perhaps foreboding in the sense that it kind of illustrates how much we depended on luck for this breakthrough, is that the hardware breakthrough itself was a fluke. So GPUs were developed for video games, and in the 2000s, there started to be gradual experimentation on repurposing. This ended up being a software mission because a lot of it required how do we repurpose GPUs to work actually for coding with some of the connectionist approaches. But GPUs were very good at parallelizing operations like matrix multipliers. In parallel, what allowed for the breakthrough in 2012 was better distribution between GPUs. It's not possible to talk about the success of symbolic approaches without touching upon the software, because for much of early computing history, up until 1994, when MATLAB finally released its first specialized deep learning library, really Lisp and Prolog dominated. And so it's only in the 1990s, 2000s, did frameworks start to emerge like Lush and Theano and MATLAB. And really, I say this because I think that in order to understand and to equip ourselves as researchers, we can't think of our algorithm as independent of the tools that we use. In fact, if we think of our own intelligence, our own brains are both hardware and algorithm. And so to think of our algorithm as intrinsically siloed from the tools that we use is perhaps a simplistic assumption. I think at the outset, always be aware of how does the software you use and the hardware you use interact with the algorithm that you choose. Open problems in research. So I believe we have, can I get a time check? So I believe we have 15 minutes left.
Yeah,
is that correct?
About 45, I think, since it's 11:15.
Oh, perfect. Okay, lovely. That's wonderful. Great. So then we have plenty of time to embark on open problems in research. So let's have some questions then, and then
I'm so sorry. 15 minutes. I don't know how to tell time.
Okay.
11:30, but we have nothing scheduled after this directly. So if people want to spill over a little bit, that's okay.
Okay, I will curb in at 20 minutes, but let me then at a cloppity pace, I'll run through open problems and research, and then we can spend 5 to 10 minutes on questions, because I think that's often the most fun part for people. So let's do that. I'll pause questions for now, but we'll bring them up at the end. So I want to briefly talk about open problems and research. I like that Bekush is getting ahead of the game. So yes, please feel free to add your questions that we should go through at the end as I go through the section, and we can bring them up one by one. For open problems and research, I do want to talk about kind of think about this continuation of the computer vision problem, because partly it's an interesting case study to understand solving one metric, but then realizing that there's other metrics you need to optimize for. So what we achieved in this change from the 2000s to CNNs is this growth in accuracy. But at the same time, these headlines alone illustrate that perhaps we want more than just high tested accuracy. My research is really centered on this. So how do we guarantee the model function fulfills other properties? And let me talk about this section, and then I'm going to really kind of surface level go over the next. But one of the things that I'm very interested in right now is this bigger is better rates in the number of parameters. This has really gripped the machine learning community. So this is computer vision algorithms, and we can see this huge growth in petaflops. This is, remember, lovely Lynette at 60,000. Well, it's kind of ballooned into massive algorithms like supervision with 60 million. And part of this is explained by the dimensionality of the inputs. And now we just have natural image data sets, which we typically feed into a model at 224 pixels by 224. So it requires more parameters. But we also see it in language models, and so our models are getting bigger and bigger. However, the relationship between the weights and the generalization properties is not well understood. So there's diminishing returns to adding more parameters. We see this jump from inception v3 to inception v4. So you almost double the parameters, but you only gain 2 percentage points in accuracy. There's many redundancies in parameters. So we find that these parameters tend to be very correlated with each other. And there's a puzzling ability where you can remove most of the weights. This is recent work I did, which shows that you can remove 90% of weights and only lose 3% of performance. And the majority of weights are used to represent underrepresented features. So we're using most of our weights to codify a small fraction of features. And why is this interesting? Deep neural networks appears to be a very inefficient way of encoding a representation. If most of the weights are redundant, why do we need them in the first place? Can we start sparse and arrive at a similar accuracy? And it's also interesting because there's a spiraling energy cost of training. So training BERT on I believe that's a GPU. Poor TPUs. So TPUs are actually more energy efficient, but I recommend you read the paper. But training BERT on GPU is roughly equivalent to a transatlantic flight. And then there's practical reasons. So most of the world is using ML in resource constrained environments. So if you want to make ML more accessible. And then also there's the attraction of wanting to really leverage all these this cheaper compute that people actually have access to. And I think what's interesting is that it's very clear to me that we're in a regime that's not sustainable. So we may be making progress, and it may be interesting to see the limit of what we can translate by simply throwing parameters at a problem. But it's almost like building a ladder to the moon. Our brain is incredibly energy efficient. And that's typically through the use of specialized pathways, our ability to simulate much of what we see. So you don't actually see me right now unless I do a very dramatic movement. A lot of what you see, if I stay fairly still, is a projected impression of what you think will be there. It's infilling. And that's largely because we don't do a full forward pass for a lot of our inputs. We try and match it with our prediction, and then if it matches, we just project. Several assumptions about deep neural networks are currently very primitive. So we initialize at random, but initializing at random is almost, our assumption is we don't know better than to initialize at random. And we do a backward and forward pass for every example, but we all know that all examples are not equal. Like if I see something that's very interesting that I haven't seen before, I typically spend longer looking at it. Or if I see something that's unexpected, I like zoom in. And this really suggests that we can reconsider some of our assumptions about how we treat examples during training. And it's very interesting open questions around how we even think about how our parameters are used. Right now, we essentially delegate all the representation to the model. And then the other thing I want to briefly talk about is this beyond top-one accuracy. So often we need interpretability tools to order and understand model behavior. There's very interesting reasons for this. So for example, here, we have an image of a cow and two images of a limousine. So which image of the cow do you think the model gets incorrect? 1 or 2? Okay, so we have a lot of 2s. Okay, yes, so it's 2. And the reason maybe you've gathered is that this is a cow in a very typical environment. It's strolling on the beach. And often our models are trained on very typical examples of cows in their pastures. What about the limo? Is it 1 or 2 that the model gets incorrect? Oops. Plenty of 2s. Okay, excellent. So this is, again, a limo on ice, which is very unusual and not part of our typical train distribution of a limo in an urban environment. And so this is interesting. Perhaps it's kind of laughable, but when this happens in sensitive domains, it can be a huge cost to human welfare. So this is 2 healthcare examples. One is skin lesions, where essentially the training data had a ruler beside certain types of malignant skin lesions. And so the model learned to pick up that those skin lesions were malignant, but of course that doesn't translate beyond that specific training data. And pneumonia, one of the hospitals in the training set had a metal tag that was typically placed amongst patients that was learned to associate with that particular setting. And in both these cases, this really impacts how the model performs across the distribution. And then, of course, we also know that parametric models often evidence disparate performance on underrepresented groups. So I'm actually going to stop after here, but I think this is also a very important area of how do we audit behavior and how do we think about interpretability tools. So let me bump ahead a little. So I'm going to pause here. I would love to invite questions. So either raise your hand or you can add the question to the chat. And then we can use the last 10 minutes to go over questions that you have, either about what we covered here today or more broad questions about machine learning.
We have 2 raised hands and 4 questions in the chat that I have down. So,
excellent. Okay, perfect. So we can go with the raised hands first.
Yeah, I think Sebastian has had their hand raised the longest. You should be able to speak now.
Oh, my bad. My cat ran over my keyboard. I didn't mean to.
Oh, Sebastian. Well, now you have to come up with an excellent question on the fly.
I'll definitely come up with a question because I did have some questions in mind. However, it's like for me, there's like a bunch of information that we've covered today. So I'll definitely come up with a question. Absolutely,
no pressure. Yeah, rogue cats understood. In fact, cats are a recurring joke in machine learning. There's an excellent paper dating from, I feel, 2013, where one of the most famous papers was about recognizing cats, and it took 16,000 CPUs, and then the next year they replicated the experiment with only 2 GPUs. So pretty interesting. Hannah says, are there trade-offs? Oh, okay, I guess we have another raised hand.
Hi,
3,
can
okay.
you hear me?
Yes.
Okay, yeah, so you were saying that underrepresented features require more weights to be in the network, like more weights are assigned to learn underrepresented features, right?
Mm-hmm.
So in that sense, is there a way for a network to know which features, like during training, to know which features are underrepresented and, I don't know, in some sense, ask us for more examples in that case, in those, having those features in them?
That's an excellent question. So this is an area of research I'm really excited about. So yes, I believe there is. I believe that this is very much open pressing research question. So the comment that I made about this relationship between capacity and features, research on that has been very recent. So I worked with colleagues on that last year, and there's another group of researchers who's working on the properties of memorization, and essentially there's a convergence that a lot of our capacity, the majority, is being dedicated to these undersampled features. Once you recognize that, what you're describing is a natural next step. How do we identify these underrepresented features earlier in training? Hopefully in an unsupervised way, because remember, a lot of these underrepresented features we don't have the capacity to label. And how do we treat them differently? How do we better use capacity? So yes, you're hitting upon pressing research agendas.
Cool, sounds good, thanks.
Yeah.
I believe,
How are you?
yeah, cool.
Hi, yeah. So I have a question about how you got started in AI and machine learning, and what inspired you to pursue the profession and do research for Google.
Yeah, it's an excellent question. So I believe I've been wrangled into a panel tomorrow night. So you'll probably, I don't want to duplicate the content that there's a panel that I was invited to with one of my fantastic colleagues, Pablo. I don't know who else is on it, but we'll be talking about careers in machine learning. So maybe I'll defer to then, but yes, I'll defer so we can have more time for other questions. But you can catch me tomorrow.
Okay, great. Thank you so much.
We have more raised hands and we have questions in the chat.
Should we, I guess, Nikita, you do the moderation you think is best. I'll defer to you.
I'll ask one question that was asked earlier that was related to a bunch of your computer vision slides. Do you think there will ever be a point that computer vision will be strong enough to fool CAPTCHA if this hasn't already happened? This was by John Rosa.
Pardon? Sorry, was that last part?
This was by John Rosa. That was just the name.
No, to fool, sorry?
Do you think there will ever be a point that computer vision will be strong enough to fool CAPTCHA if this hasn't already happened?
CAPTCHA as in?
So when you are entering passwords and you have to select the images that have
I see.
Yeah.
I don't know. I guess as two. So typically we centered so the first part of CAPTCHA is fairly straightforward, where it's to identify an object. But this is in the realms of security, but progressively there's been more and more interactivity. So often you'll be prompted with a second, and then you'll be prompted to click something, and those type of interactions are harder to pre-codify. So the recognition task itself, yes, that is fairly straightforward. But you have to anticipate what the possible objects are. So you would have to pre-train on a variety of different typical CAPTCHA questions.
Hello. Sorry. Hi, my name is Barack. I had a quick question. So I was wondering, with like lower quality images that have like very minimal like change in RGB. So like if you have like a white dog inside of snow, playing on snow, basically, how does like AI like distinguish the two? Like how does the AI distinguish like a dog from like the snow?
Yeah, it's a really good question, actually, because the reason why I say that is that it's interesting because presumably it's difficult because the way that we see the world is log scale. So as I mentioned earlier, it takes a noticeable change for us to register. So something like a dog on snow is actually very tricky for us to decipher. But what's interesting is that convolutional filters don't have the same hiccup. In fact, convolutional filters have shown the ability to take advantage of pixel-wise differences. This actually is both an advantage and a disadvantage, because it's also why we can craft what we often call adversarial LP norm attacks to essentially trick a model. But it's also why, if you have a sufficient amount of data of dogs on snow, a computer vision model is often remarkably good at classifying. And that's one reason why, for things like I mentioned the retinopathy example earlier, for these very essentially tricky medical images, we've shown that convolutional neural networks can pick up features that human eyes simply cannot. And that's because it doesn't have the biases that we have in our perceptual system.
Okay, thank you.
Shinyi, I believe you can unmute yourself. Yeah.
Yes, hi. I just want to say thank you for being here. I definitely learned a lot about AI and machine learning so far, and I wanted to ask, how do you think that computer vision could help marginalized people in a costly way? Because that's something I'm pretty passionate about, and I wanted to know like what you thought about it.
Yeah, that's an excellent question. I purposely tried to profile some of the use cases from a lot of both my students in Africa. So I grew up in Africa. And so a lot of why I'm interested in not just how do we make models fulfill test set accuracy, but these other properties is that I think it's very exciting for computer vision models to be applied for things like healthcare in many of the communities I grew up in. And the strength of that is that really, if what we are imparting with the computer vision models is we're processing information which is typically very expensive to collect. So there's often certain settings where to collect information in the form of surveys or to collect information in the form of digitalized input data is very expensive. And now we can leverage other types of input domains in order to provide useful services. I think a good example in this vein is a lot of the work on satellite imagery. So my colleague recently did a fascinating project on spatial dynamics in South Africa. So South Africa had an apartheid regime for many years, where essentially you had segregation based upon race. And she recently, with other colleagues, leveraged satellite imagery to show that many of the residential areas are still adhering to this apartheid time segregation. So there's fascinating use cases like that. What I would say is that with tooling also comes this idea of responsibility. So we need a lot more people also thinking about how do we anticipate the trade-offs of deploying to some of these environments where often we're using a resource-constrained environment. So often we're processing data which it hasn't been trained on. So there's also a huge use case for better data collection, so it represents a lot of the communities we're serving. That was a long answer. I hope it was slightly helpful.
Yeah, it was, Lori. That was really interesting. Thank you.
Absolutely. Let's do two more, and then I'll let you all go to your lab.
Yeah, I unmuted, sorry, one more person, Omina. You ask your question, and then I believe we need to make an announcement because Slack is completely down, and we made an alternative with the Discord server, but go for it, Amina.
Okay, hi, can you hear me?
I can, yeah.
Okay, I'm not sure if this is gonna come out the way I want it to, but I'll just ask. So I was sort of wondering, like, as far as people who are like working in AI or machine learning, what are your thoughts, or do you believe that they are sort of like the initiatives when it comes to why people want to, you know, progress AI, progress machine learning, like, I don't know how to phrase this, but basically the intersection of, you know, consciousness, neuroscience, and artificial intelligence. Like, sorry, I should have thought of this more before I asked it.
No, go for it.
I guess I'm not trying to like, I'm not asking about like the ethical implications of artificial intelligence, although that is related to my question. But do you think that machine learning and artificial intelligence is trying to close the gap between, you know, the methodologies, but also philosophy, like, you know, taking into account consciousness? How can we make machines conscious? Are people really worried about that? Or are they really just worried about, you know, I guess bigger is better, the whole thing that you were talking about earlier? Sorry if.
Yeah, I mean, it's actually a fascinating question, because I think what you're really asking is the first part of this presentation was all about this kind of goal that's quite ambitious. And then in the second part, it kind of comes back to earth, right? And I started talking about parameters and the open research questions we have. And perhaps what you're asking is, what is realistic? How connected are those principles? Do most people working in the field, do they think about the quest for AI every day? I would say that the truth is that there's very interesting feasts and famines in research. And so for the last 10 years, we've had this breakthrough of deep neural networks, and it's been largely a lot of productivity research-wise, thinking about how to think about the boundaries of this breakthrough. And I would say the growth in parameters is one aspect of that. We're trying to figure out the limit of just throwing parameters at a problem. That's an important limit to figure out. But whenever you're close to a plateau in terms of the big breakthroughs, people start doing riskier research directions. They reassess what is my research agenda, and you start to have a more interesting diversity in research contributions again. And this is where I think people, the idea of what is your ultimate goal comes more into play, which is not necessarily human consciousness, because as I mentioned earlier, I don't adhere to the belief that it needs to be intrinsically principled on all human intelligence. But this idea of we want to impart useful skills to machines, and right now we're in a regime which is quite far from that goal. So at the very least, it forces us to assess well, what is realistic for our current tooling. And the exciting part about this is that computer science history it's but a young child. I mean, we haven't been working on this problem in a meaningful way with the right tools for very long. And so in many ways, it's a very exciting time to join the field because the distance from what I described as our approaches, our current present day approaches, and the ultimate goal is actually fairly large. There's not, the real implications in terms of ethics are much more on the applied side of our ready-made technology, but not necessarily in terms of consciousness by any means. That's not something that is what we talk about every day. I hope that got somewhere towards what you were asking.
Yeah, thank you.
Of course, yeah. And I'm going to pass over to Nikita for a very important announcement.
Yeah, sorry, since we are over time, Swapnil is going to make a quick announcement about how we're going to try and communicate since Slack is temporarily down worldwide. Go ahead, Swapnil.
Thanks, everyone. Firstly, thanks so much, Sarah, for joining and getting through all the technical issues. The Discord link is what I'm posting in the chat now. So the link should allow you to join this Discord channel. Okay, I see. Nice to see the responsiveness. With that, the point being, Slack shouldn't be down for really long, so we will hopefully go back to it during the week. But Discord is also new for us, so if there are issues, please just ask us. We'll be happy to respond. Don't stay out of the loop because that just ruins the experience for you. The other thing is, I forgot what the other thing was. There was another thing for sure. But yeah, I'll be posting a link. So as Sarah mentioned, we have 2 panels. She's part of one of the panels as well. So I will be crowdsourcing some questions so that all of you get a chance to ask the panelists specific questions about given their background. Please go through their bios. They're all on the website, so it's very easy for you to access. So give us the questions you have for the panelists. We'll pre-filter them. There will also be an option to ask live questions, but just in case we have too many of them, we might not be able to get to yours if you only ask live. So fill in your questions in the Google form and join Discord. Thank you.
Yeah, thank you so much, Sarah, for joining us and going through the many Zoom gymnastics to join. That was our first lecture for the day. Your labs start at 1. Once again, make sure you go to the correct Zoom link. And in the meantime, I'm sorry we did not get to everyone's questions. I've tried to note them all down. But ask them in the Discord, definitely ask them in the Slack once that's back up and running. And in the meantime, there are 2 office hours that are currently being held. So if you have a specific question about the lecture or machine learning, I would recommend maybe trying to attend one of those. And that's all. We'll see you all soon. Goodbye.